In this lecture, we're going to go over power, time, rate of energy transfer by work. If there are observable forces in our system, the power involved is equal to the product of the velocity at the point of application and our force. If we remember, our power is our force times our velocity vector, where a dot above a variable means it's a time rate. Integrating power gives work, so work is equal to the integral from time 1 to time 2 of our power with respect to time, which is the integral of our force dotted with our velocity with respect to time. The same sign convention for work applies for power. So power is positive if we have work out of the system, and power is negative if work is into the system. So the units of power are the joule per second, which is a watt, which has a symbol W. It is the foot-pound per second, or BTU per hour, or another unit that we use is the horsepower, which is HP. There we go. So to review our mechanical concepts of power and work, we're going to do an example where a steel wire is suspended vertically and has a cross-sectional area and an initial length, and it's stretched downward by a force. The normal stress in the wire varies linearly according to our stress is equal to some constant times our strain, where our strain is given by our final length minus our initial length over our initial length. C is a constant, it's the Young modulus of the material. And assuming the cross-sectional area remains constant, we want to obtain an expression for the work done on the wire and evaluate the work done on the wire in foot-pounds and the magnitude of the downward force if we know the value for a bunch of our constants. So where are we going to start? Good, I have a blank page. So what do we know? We know we have a wire and it's suspended vertically. And that wire is stretched. We're trying to find an expression for work and the work done. What can we assume? Well, we can assume that the cross-sectional area is constant. We know that stress is equal to C epsilon, and epsilon is equal to X minus X naught over X naught. C is equal to 2.5 times 10 to the 7. X naught is equal to 10 feet. X is 10.01 feet, and A is 0.1 inches squared. So, how do we solve our problem? We have work is equal to the integral from x naught to x of sigma A dx. And since work is done on the system, this is going to be negative. And of course, we had the fact that sigma is our force divided by area, which means our force is sigma times our area. So I'm going to relate stress and strain. So sigma is equal to C epsilon, which is equal to C times x minus x naught over x naught. I'm going to plug that back into my integral. So I'm going to have my work is minus my integral from x naught to x of C x minus x naught over x naught times A dx, which is equal to minus the integral from 0 to epsilon of C epsilon A x naught d epsilon, which is equal to minus C A x naught epsilon squared over 2. So if we plug in our values now, we have our work is equal to minus 2.5 times 10 to the 7 pound force per inch squared times 0.1 inches squared times 10 feet times 10.01 minus 10 divided by 10 squared times 0.5, which tells us that our work is equal to minus 12.5 foot-pounds. That's it for this lecture. It's basically a review of concepts of mechanical work and power that we should already know. In our next lecture, we're going to go over modeling expansion and compression work. So we're going to continue to expand our understanding of work and energy.